Today we're going over all the vocab associated with circular motion. So during this part, you should have your notebook to write down things, but I'm gonna ask you to hold off if you need me to rewind slides. Hold off till the end since I'm recording this. So for circular motion, one new vocab word is actually one you've heard me use today and probably earlier in this year as well, is time period. Time period is the time to complete one cycle. If I'm talking about the Earth going around the sun, the time period is 1 year. But if I wanted to use that in an equation, I would need to take 1 year and turn it into some large number of seconds. So time period is just going to be the time for one complete cycle. That can be in circular motion, like an orbit, or that could be not in circular motion, like a pendulum going back and forth. It doesn't even have to be physics related. Time period is associated with secular things, things that occur repeatedly. So the time period of a human heartbeat would probably be something along the lines of 1.5 seconds. Every 1.5 seconds, your heart beats. And then I had you go take that and calculate tangential speed.
Launch wave 2 is beginning at this time. Please report to your assigned location for
So
launch
close.
wave 2.
Lunch is coming. I know. Okay, so then next, I had you guys do tangential speed. And tangential speed is just like regular speed, except it's the distance along a circular path. And we call that distance along a circular path a circumference. So tangential speed is distance divided by time. It's just that distance is going to be a circumference. So here's one equation I will definitely put on your equation sheet for you. Tangential speed is circumference divided by time period. So this one with a box around it, that one's going to be on your equation sheet. Just a special thing, make sure that's the time for one cycle. So if I tell you it does like 10 cycles in a minute, I would want to put in 6 seconds because that's the time it takes to go around once. So for tangential speed has to do with how big of a circle the object makes. And so I have a quick demo for us that we'll look at on the computer, and then if we have time, we'll look at in person. So let's say we take something like a record player. If I pick a point that's close to the center of the record player, like right at the edge of the label here, that point has a small radius, and so it travels a small circumference. That means it travels a small distance in the same amount of time. That means things that are close, things that have a small radius, travel slowly. So, relationship here. That equation means that if radius goes down, speed goes down. In fact, can you find me the point on this record player that has 0 speed?
Middle?
The middle, the center. That point in the center has 0 speed because it travels 0 distance. And the opposite is true. The opposite statement would be like, all right, well, if I have a large radius, then it travels a big distance and has to travel quickly. So if you look at this larger radius circle, it has to travel a longer distance and so travels faster. We've got a record player, and it's got 3 caps on it: pink, blue, and purple. And let's see if we can make it play music. It's so pretty, right? The pink marker cap in the center of the record is unmoving, but blue and purple go a much longer distance. Purple has to travel faster to make the same time period. In fact, if I took this cap and put it to the outside edge, it has trouble even staying on. And that's because it's going so fast, it has trouble completing the motion. And the point of that demo is that things that are close to the center travel slowly. Let's say I have something like the person running in this circle. Poll question. Which point of the runner has the largest tangential speed? Is it their head, shoulders, knees, toes, or all the same? Kids at home, answer the question in the Zoom poll. Kids here, I'm going to call on you in a sec. Kids watching this later at home, remember, we're trying to figure out which tangential speed is greatest. His head, shoulders, knees, toes, or all the same. Pause your video, and then when you come back, we'll figure it out. Now, if you said all the same, they have all the same time period, right? Because like it takes the same amount of time to make the circle, but the toes travel the bigger distance, right? Look at his head, right? His head barely moves, right? This has got to be like really disorienting for him, right? So his head barely moves. His head has the lowest tangential speed and his toes have the highest. So there's a related term to tangential speed. That related term is tangential velocity. And it's going to have the same difference that regular speed has to regular velocity. So if you remember from speed and velocity before, speed was like distance divided by time, and velocity was distance divided by time with a direction. So tangential velocity is just going to be speed with a direction. So I'm going to take my tangential speed and add on what direction the object was traveling at the time that you measured it. Now, that means that it depends which point in time you pick. If my object is going in a circle and I pick the top of the circle, it's traveling in a different direction than it was at the bottom of the circle. Tangential velocity is the speed plus direction. And here's how we remembered the direction. It actually has it in the name. Tangential as a direction means tangent to the circle. Now, here's how I draw this. It's got to do two things. It's got to be perpendicular to the radius and in the direction it was already moving. So let's say I take the moon right when it passes this little orange point. What I want to do is I want to identify the point in time and in my head, or if this is like on paper, draw the radius on paper. Right? If you were physically like doing this homework on paper, then I would say like grab a corner of a paper and put it up to make sure you get a right angle here. Because I want to draw my tangent line as perpendicular to the radius. So that's about as close as I got it, guys. Perpendicular to the radius. So I got that. Check. And in the direction of motion, this moon is traveling up and to the left at that point. So my tangential velocity's direction is up and to the left. It meets both criteria. It's perpendicular to the radius and in the correct direction. So I've got some questions for you, and I'm going to have you vote in Zoom, and kids here, I'll call on you. And kids who are watching this later at home, I want you to pause the video after each of these questions, think about your answer, and then press play again. So here's the question. When the electron has reached that bottom point, what direction is the tangential velocity? Is it left, right, up, or down? Pause the video now and see if you can figure it out, right when it reaches that orange spot at the bottom. Now, here's why it's left, guys. So imagine I draw the radius, then I draw the tangent line.
Oh, it is left? That was right.
It is left. Everyone was, well, lots of people were correct, which is good because this is the first try, right? We're going to try a new one in a sec. So it's left because left is perpendicular to the radius, and that's the way the electron is traveling. If you said right, I think you were like, all right, it's either left or right. Let's coin toss between one of these. What about this one? I've got a car, it's traveling around one of those intersections in downtown Glastonbury that I'm sure you guys just love. What direction is the tangential velocity of the car when it's at that point? When it's at that like pinky orange point? Choices are left, right, up, down. What direction is the tangential velocity? If you're watching this at home later on, pause the video right now and see if you can figure it out for your own. All right, so we had 13 kids total say up, a few left and a few rights, but just to double check, the radius is left and right. So that means the velocity has to be either up or down, but the car is traveling upward at that point. A thing to note for tangential velocity is that it's always changing direction. Like sometimes it's going up and sometimes it's going left and sometimes it's going down and sometimes it's going right. That must mean it's accelerating. And I know this was a while ago, but our original definition of accelerating meant three things. It could be speeding up, slowing down, or changing direction. And this is that third type, changing direction. New vocab word, this is called centripetal acceleration. This is acceleration that causes a change in direction without causing a change in speed. If I were like doing donuts in a parking lot, I would have a big centripetal acceleration because I'd be changing direction really quickly, even if I go at constant speed, which is why if you're in your car doing donuts, you feel like you're getting pushed around, right? You'd feel something because you're accelerating. We'll talk about what it is you feel later, but new vocab word, centripetal acceleration. It is a vector, which means it's going to have direction, but its direction is super easy to figure out. Tangential direction always meant like, perpendicular to the circle and in the direction of motion. But centripetal as a word literally means center seeking. So from whatever point you are at the circle, the centripetal acceleration seeks the center of the circle. It points to the center, right? So if this is your point, and I know it's hard to see, I'll make it bigger for the next class. If this is your point, what direction is centripetal? What direction is it to the center of the circle? Is it up and to the right? Oh, give me a second to give you the correct slide number. There we go. Launch poll. Is it up and to the right, up and to the left, down and to the right, or down and to the left? Centripetal acceleration is center seeking. So I'm going to take this point. And what direction is the center of this circle? Is it up and to the right, up and to the left, down and to the right, or down and to the left? Kids watching this at home, pause the video and see if you get your answer right. Pause it right now. The class, we said, for the most part, down and to the left. Down and to the left would be towards the center of the circle. And nice thing about centripetal, for anywhere in the circle, it always just points to the center. So whenever you see the word centripetal, it means center seeking. It's pointing towards the center of the circle, wherever that is. So that was down and to the left. If you said up and to the left, you might have been thinking tangential velocity. Right? So equation for this guy, that's going to be speed squared over radius. Equation that you guys are going to be good at solving since we've already done lots of equations with squares before. You guys are actually really good at the substituting and solving things. All right, so I'll show you an example of how to calculate this because it's the first time you've seen this equation. Then I'll show you a demo of like what it looks like in real life. All right, so centripetal acceleration, let's say I do like a one where I try to trick you, because sometimes I do ones where I try to trick you. So let's say in this case, I've got a bicycle and the wheel has a diameter of 0.7 meters. We know the tangential speed, so I know V, cool. And I want to calculate centripetal acceleration. Do you guys see the trick that I put in there? And it's not that I'm trying to be mean. It's just like diameter and radius are similar quantities. I gave you the diameter, but you need the radius. So you would have to know to divide by 2 to change the diameter into radius before solving this out. Okay. So my wheels have to accelerate 71 meters per second squared in order to change direction fast enough. Now, what that would feel like if you were a bug on the tire, do you see this like little yellow point? The bug would be experiencing an upward acceleration, but its body wants to continue in a straight line. So as a result, the bug would feel like it would get pushed to the outside of the wheel, which bad news bears for the bug because that means probably get crushed by a bicycle. So mathematically, you can actually math this out. This is called a von Braun space station. It is one of the most popular ideas in how we imagine we'd have to create like space habitats for humans in the near future. And just as a heads up, we're like relatively close to that level of technology already. So here's what we're imagining. So we want the space station to have 1g of centripetal acceleration. So its inhabitants feel like they're on Earth. Our bodies have evolved to live in 1g, so it does bad things when we're not. So what I want you to do is grab your calculator for me and try this problem out. If I have a space station where acceleration is equal to 9.8 and the radius is 28 meters, how fast does it need to go?
For kids at home, pause this video and do this calculation out. All right, choices here. Is it a speed of 16.5 meters per second? Is it a speed of 87.4? 244 meters per second? Or none of the above? If it's D, none of the above, is it impossible to calculate speed without time? Pause this video and calculate it out for me.
So let's say I take my 9.8, I'm going to multiply by 28 to the other side, square root everything to get the speed.
So if you said A, 16.5 meters per second, you'd be correct. If you said B, 87.4 meters per second, that means you accidentally did order of operations wrong. In step 2, you square rooted 9.8 instead of multiplying by 28 first. You need to do multiplication before a square root. If you said 274, then you forgot to take a square root on the last step. So the correct answer was A, 16.5 meters per second. And it turns out you can calculate speed without knowing time. Just because the acceleration equation doesn't have a speed equals something in it, doesn't mean I can't use it to solve for speed as one of the missing variables.
If something is accelerating, that must mean there's a force on it. And there's a special name for a force that points towards the center of a circle, just like there's a special name for the acceleration that points towards the center of a circle. Right? In this case, we call it a centripetal force. And centripetal force could be any type of force. It could be friction, gravity, tension, whatever. It could be any type of force, as long as it's pointed towards the center of a circle. If it's pointed towards the center of the circle, what it does is it causes the object to move in circular motion. So when the pig was flying around this room, the force pointed towards the center of the circle was tension. That means that your centripetal force and centripetal acceleration are always in the same direction as each other. They're always pointed to the center. And any force can be centripetal. Special things, let's see. It is a vector. It has a direction. The direction towards the center of the circle. So a centripetal force is a force that's directed towards the center of the circle. And it could be any force. So let's say I have this roller coaster example. I'm going to ask you in a poll, which force is centripetal? Your choices are tension, gravity, friction, normal, electrical. Which is the centripetal force?
Pause the video now and see if you can figure it out on your own.
All right, force that points towards the center and always points towards the center. That would be the normal force. Gravity points towards the center for a moment, but it doesn't always point towards the center. What about this one? Which force is centripetal now? If this is a roller coaster and you're on the top of the circle, which force points towards the center? Is it tension, gravity, friction, normal, or electrical?
Pause the video right now and see if you can figure it out on your own.
So in this case, if you're on the outside of the roller coaster, then gravity is your centripetal force. If you're on the inside of the roller coaster, then normal is your centripetal force. You're going to take it from the scenario. All right, I'm going to give you like 30 seconds on this one. Which force is centripetal? Moon goes around the Earth. Your choices are tension, gravity, friction, normal, electrical.
Pause the video right now and see if you can figure it out on your own.
So we've got gravity as the force that is centripetal in this case. Okay? So it's not normal force. Normal force would require like some solid object is pushing the moon towards the Earth, right? And that'd be really funky. All right, how about this one? Another 30-second one. Which force is centripetal? Electron goes around a proton. Choices are tension, gravity, friction, normal, electrical. And think, if I'm asking so many of these, it's because I'm going to ask you like at least one of them on the test.
So if you're watching this at home, pause the video and see if you can figure it out on your own.
Now, technically, there's two correct answers here, but one of them is a much more significant force at that scale. All right. The kids at home are pretty much split between gravity and electrical.
Seems like a good split to me.
It does, because both of those are centripetal. It's just that the gravitational force is super small compared to the electrical force at that scale. So they are both correct answers. I probably wouldn't choose one with two correct answers for your test, though. Which force is centripetal? Tension, gravity, friction, normal, electrical, same choices as before.
Pause the video and see if you can figure this one out.
Cool. We've got 91% of the kids at home say that this one is tension. And I'm going to leave you as the last one is a tricky one. What is the centripetal force? I've got a car making a turn. What is the centripetal force? Is it tension, gravity, friction, normal, or electrical?
Pause the video and see if you can figure it out on your own.
Most of us got it anyways, which is excellent. Kids here, what were you guys thinking? Friction. Yeah. And think about it, if you were driving and there was no friction, you wouldn't be able to make the turn unless friction was there. And if you're having trouble picturing it still, lots of people think normal the first time that they do this one. Let's check out the picture on the board behind me. This is what your car looks like as it makes a left-hand turn. Normal actually doesn't point towards the center of the circle. Gravity doesn't either. Friction has to point to the left in order for your car to make a left-hand turn. So friction is the centripetal force pointing towards that axis. So the centripetal force equation then will be our last new equation for the day. This will let you calculate everything in the first 3 pages of the homework. So if you're a work ahead person, you're like, homework is due Saturday. Once you've got this equation, you've got everything you need to solve the first half of the homework, right? So new equation for you. Centripetal force is mv squared over r, where v is that tangential speed that we just learned how to calculate last block. The nice thing about this equation, like the thing I like about this equation, is since any force can be centripetal, I can use this to calculate, I can use that equation to calculate friction in a car driving problem. I could use that equation to calculate tension in this pendulum problem. I could use that equation to calculate the electrical force of attraction between the proton and electron without having to pull out like all the old equations. Another thing that this equation means is this also means the minimum force that your system needs to apply in order to go in a circle. So let's say this occurs, right? Let's say that I've got this minimum force. I go like calculate mv squared over r, right? And the system doesn't put in at least that much force. If it doesn't put in that much force, then the object will just go in a straight line. Like an object in motion stays in motion. And that's why if I did the water demo wrong, in one year I did do the water demo wrong. The water demo, I like spun the thing, right? But it hit the ceiling grid, and so the cup stopped. That means the centripetal force wasn't being applied. So my water was an object in motion that stayed in motion and sprayed like across the whole classroom. It didn't spray me because I was below it, but it sprayed like across the room, which was good times. I was fine. So how about, let's show you how to use this equation. And then I'll show you that sometimes there's like extra information that you don't need till the end of a problem, right? So let's say that you're out driving your car and it's a 1,000 kilogram car. It's going 20 meters per second, radius is 15 meters. Now you might see that it asks for calculate the minimum friction force, but I don't want you to go pull out the friction equation. I want you to use this mv squared over r. And you can tell because I didn't give you a coefficient of friction. And I see there's a 900 number. I'm going to hold off on that number until the very end, right? So I go substitute mv squared over r. And I find that the minimum centripetal force that my car needs to apply is 26,667 newtons. And that sounds like a lot, but it's a big car and it's moving quickly. And that's a really tight turn radius. Normally, let's say you were doing a track. Imagine like running track and field. Your turn radius would be like 25 meters, something like that. But a car radius would need to be like 100 meters to make a turn easily. So your car is only putting out 900 newtons of force. It doesn't meet this 26,000 Newton requirement. So if your car puts out more than that limit, that's great. Your car makes the turn, and that's what we want. Okay, but if your car doesn't do it, it only puts out 900 newtons of force, and the force needed was 26,000 to make the turn, then the car obeys Newton's first law. It keeps going with the same speed and direction that it had before, right? If it doesn't put in enough force, the car is an object in motion that stays in motion. Now, it turns out that like object in motion thing, it creates this kind of misconception. Okay? It creates this misconception called centrifugal force. And that's a word I'm sure you've heard. But a centrifugal force is not a real force. It's not actually there. Now, compared to centripetal, centripetal means towards the center. Centrifugal would mean away from the center. And I want to point out that there's no real force there. So let's take a look at this kid. And I don't know what's up with how this video was shot. Do you see like the screen moves back and I don't know how that happened. This kid that is so nice to his sibling. Now his sibling is probably
that's called that's a stabilization technique where you basically move the frame of the photo itself in order to focus on a central subject.
Yes.
They could have just cropped it, but
They could have, but they didn't.
It looks like
Oh.
something I totally do to one of my brothers.
Probably.
Eat him.
In fact, I'm pretty sure that, like, when I was little, I'm pretty sure we did things like this. Maybe not exactly the same, because that appears to be, like, particularly mean. Like, that's a pretty little kid. So now, see how the girl's body looks like it's being pushed away from the center of the circle. But I want to point out her path after she lets go. The path after she lets go isn't away from the center of the circle at all. The path is tangential. So let's look at a better one, right? So this is a new vocab word. It's not a real force. There's no related equation that goes with this. The centrifugal force effect is this feeling of being pushed away from the center of a circular motion, but that's only because the girl's inertia causes her to move in a straight line. Now, it's not a true force because it doesn't cause acceleration. Just like, you know how inertia is not a force? The centrifugal force effect is not a force. So let's take a look at this example. This person like spun a glass around with a marble in the center. We can see the circle. And let's see the path it took. If it took a centrifugal path, it should go away from the center of the circle, but it doesn't. Instead, it goes along the tangential path, the one that's tangent to the circle, like the tangential velocity we did in the first block, right? That's because as soon as that force disappears, well, then the marble is an object in motion and it stays in motion and it travels in a straight line. Now, to be fair, the reason like people confuse this and think there is an outward force is the marble does at the end up farther away from the center of the circle than it was to start. But not because there was an outward force, but just because the cup went away and so the ball kept going in a straight line. Similarly, I've done this demo before with like a hula hoop and tennis ball. You can do that one at home. The ball's inertia makes it travel in a straight line, but it doesn't get pushed outward. Okay, a particularly cool demonstration of this. Let's see if I can find it. There. Okay, so what this guy has in this demonstration, he has a drill with a bunch of sparklers attached to it. I don't know why he's not wearing eye protection at this point. I feel like that's inherently unsafe, right? But if you watch the path of the sparks that are leaving the sparkler, as soon as the sparks aren't attached to the sparkler anymore, they don't get pushed away from the center of the drill. They go in their tangential path, and you can see those kind of like sparking off on the sides. If you've worked with like woodworking equipment before, you know the sawdust always gets pushed tangential to the circle, but not outward away from the center, not centrifugally. So this centrifugal force effect is actually how a centrifuge works. By spinning really, really fast, let's say you're separating out like components in a solution, the heavier components go to the outside of your glass because those have more inertia, more mass, more inertia, more centrifugal force effect. The more that mass wants to go in a straight line. So here are the two cool videos that we're gonna skip for time, but you can watch on your own. Okay, video number 1, what if the sun disappeared by Vsauce? Or what if the earth stopped spinning, also Vsauce? Spoiler alert, if the earth stops spinning and we're all objects in motion traveling at about 10,000 miles an hour, bad things. I couldn't survive a 10,000 mile an hour car crash. Neither could anyone else. We'll go with.
So now would be a good time to take the notes you just took and go apply them yourself. Try out these concepts on your own Homework 5.1, that's due Saturday, January 9th. Try them out on the first 3 pages. You should be good to go. And best of luck!